Hello everyone, welcome to lecture 27 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on optical magnetic elements. Here is the lecture outline. We will discuss about optical magnetic elements and we will also see in details a pair of metal strips that can work as magnetic metamaterial. So, in this lecture we will discuss about different routes for pushing the operational frequency of magnetic metamaterial into the optical regime. So, the basic principle behind these designs is that the unit structures can support a particular eigenmode with a circular kind distribution that gives rise to magnetic moment. Okay. So, in early 2000 various structures have been basically proposed to achieve magnetic response at higher and higher frequencies, because that is where the challenge lies, right. So, such a magnetic moment that can come from circular kind distribution can introduce resonant behavior for the structure. Okay. So, we will see that the magnetic moment is parallel to the incident magnetic field and this gives rise to permeability greater than 1 for the frequencies below the resonance frequency. On the other hand, you will see that above the resonance frequency, the magnetic moment is basically anti-parallel to the incident magnetic field. That means, it is in the opposite direction and that produces an effective permeability less than 1. So, in order to obtain a metamagnetic response at higher frequency, that is means metamaterial response at higher frequency for the magnetic permeability, without playing the trick of inclined incidence, okay, which we have seen earlier for the terahertz metamaterial, different variations of the splitting resonators can be used and that is what people have seen, right. So, one of the most important designs for achieving magnetic resonance toward optical regime is basically based on arrays of single SRRs which are lying in a plane perpendicular to the wave propagation. Okay. So, in the standard SRR operation, a magnetic field normal to the SRR plane will be required to excite the magnetic response, and in contrast the single in plane SRR can also act as magnetic dipoles without any involvement of the incident magnetic field. So, this one is basically coming because of the electric field. Okay. So, we will show you the details of these two things together, okay, in the next few slides. Now, this particular innovation has basically helped push the magnetic resonance into the optical regime. So, this particular figure illustrates the different orientation of single SRR arrays which I was talking about with respect to the external fields which are also shown in each of these figures. So, the first figure, figure A, basically shows standard SRR operation where you will see the magnetic dipole can be excited by the external magnetic field itself, because the field is in this direction, okay, and these SRRs are basically normal to this field. Now, the major limitation in this kind of a design is that there are fabrication difficulties, because you have to, this kind of rings are basically perpendicular to this plane. So, when you try to construct these structures using micro and nano fabrication, there are challenges coming from alignment and scale constraints. Okay. So, this vector clearly tells you the way the field is interacting with the structure. You have the magnetic field in this direction, you have electric field in this direction, and the field is falling normally on this particular substrate. Now, there are other two configurations also possible, which I will discuss briefly. So, here you can see in figure B and C, these are also SRR arrays. Now, these are not sticking upwards from the substrate, rather they are basically lying on the substrate, and that is compatible with the standard lithography and deposition techniques. So, what you will see here in this particular configuration that you have the electric field in this direction and magnetic field in this direction, right. So, figure B is particularly interesting because here what you will see that the electric field is basically parallel to the gap bearing arm of the SRR, right. So, that will basically give you a asymmetric current distribution or asymmetric current mode in the two arms of the rings, and because of that a magnetic dipole can be obtained. Okay. Now, in this both cases magnetic field is parallel to the SRR. So, it is not inducing any magnetic dipole. So, who is inducing the magnetic dipole in case B? That is the electric field, because this electric field which is aligned to the gap bearing side induces asymmetric currents in the split ring resonator arm, okay, and that is giving you the magnetic dipole. Now, if you see here in figure B, here the electric field is basically polarized along the two arms. Okay. So, in that case symmetrical or identical currents are basically excited on the two arms of the split ring resonator. So, in that case no loop current will flow and you cannot generate a magnetic dipole. Okay. So, this is the structure that will not give you any magnetic moment at all. So, this is something interesting to understand, that in the first case the magnetic field was exciting the magnetic dipole. In this particular case the electric field is exciting the magnetic dipole, but in this case the electric field is not doing the excitement of the magnetic dipole, right. So, this will not show any kind of magnetic moment. Now, let us go into details of this optical magnetic elements, and let us see how we can understand the resonance of this kind of structures using equivalent LC circuit model that will allow us to correlate the resonance frequency with the physical parameter of the structures. Okay. So, this is the case of a single SRR split ring resonator as magnetic element. So, beside the current symmetry considerations, the underlying physics in this planar SRR can also be interpreted using this kind of a equivalent circuit model, okay. And the discussion closely follows the work of metamagnetics at 100 terahertz, right. So, as discussed earlier as well, a split ring resonator can be represented as a LC oscillator. So, you will see that the ring here basically acts as the inductor L and the gap gives you the capacitance, right. So, for such an oscillator there are basically two means of exciting the resonance. The first one is this one which you have already seen, where the magnetic field vector must penetrate the inductor, okay, that is a coil, and that will give you the magnetic moment. Okay. And in the second case the electric field vector should align with the gap. Okay. So, that is the, you can say that the electric field vector must be aligned normal to the capacitor plate, that is the surface of the cut, and that will also give you the magnetic moment. Now, the third case obviously is not doing any good, okay, because in this particular case neither inductor nor capacitor aligns with the external fields, and that is why you do not see any kind of resonance from this kind of structure, right. So, what is important to remember here, that these two will give you some resonance. This is a direct excitation from magnetic field, this is a excitation of magnetic dipole from electric field, okay, but this one is not giving any resonance behavior. So, now let us look into the structure where people have fabricated this, okay, and they have shown the magnetic resonance with this case B, that is electric field excitation. So, obviously the electric field has to be excited along the gap, okay, like this. So, this is the solid line that shows you this polarization, okay, and here because of this they were able to excite magnetic moment or magnetic dipole at the mid infrared wavelength of 3 micron. Okay. So, this is the result of an experiment where the split ring resonators are typically having dimensions of 320 nanometer. Okay. So, the figure clearly shows that you have the red one is the transmission, the blue one shows the reflectance spectrum of this kind of an array of single split ring resonator, and these are the two polarization you have considered. So, one is this parallel polarization, the other one is this orthogonal one. So, let us study this. Here you can see clearly that you have this magnetic resonance, but as soon as you change the polarization to 90 degree, you are basically now along this dotted direction, which is also shown here, and here you can clearly see that the resonance, the magnetic resonance disappears completely, and that is in very good agreement with what we have just discussed now analytically. Okay. Now, these are in mid infrared wavelength, so much longer wavelength. So, you want to shift it towards visible range. So, what you can do by further reducing the size of the SRRs, magnetic resonances based on this principle have been achieved from far infrared to the long wavelength end of the visible spectrum. So, you are actually getting closer to the optical frequencies. Now, it is important to note here that this kind of electrically coupled magnetic resonance is basically an indirect one, and it is inevitably weaker compared to the magnetic resonance that is excited directly by the magnetic fields, right. So, the retrieved effective parameters show that you have got very minimal value of effective permeability around this 3 micrometer range, and the value is typically around 0.8, which is close to that of the non-magnetic medium, right. So, this is a major reason why this metamagnetics in planar single SRRs cannot be used in many interesting applications, something like artificial magnetism or negative index materials or electromagnetic cloaking, because the permeability that you are getting is very low. Another serious drawback of this kind of planar SRRs is the background of the geometrical scaling and the subsequent saturation of the resonance frequency. So, you cannot keep on scaling it down and move the resonance frequency to the optical regime or even higher frequency, that will not work. So, this saturation basically effect fundamentally this saturation effect basically fundamentally prevents the SRRs from providing magnetic response at the true optical frequencies, which is basically the visible range. Now, the scaling background of this kind of single SRR is described mainly by linking to the kinetic energy and the self inductance of electrons, which basically come from the resonance behavior of the noble metal that you are going to use in the optical frequency regime, right. So, these findings are basically supported by equivalent circuit analysis, and saturation effect comes out to be an intrinsic property of an SRR as a resonator, and it is basically independent of how these split ring resonators are basically getting excited, right. So, the analysis will apply to both the planar SRRs that are electrically coupled magnetic response, as well as for the split ring resonators which were sticking out where you are actually using the magnetic field to directly excite the magnetic resonances, right. So, saturation effect is basically intrinsic property, and it is completely independent of the kind of excitation you are using. Now, let us look into this resonator in terms of its physical properties in more details. So, as we consider this single split ring resonator, which basically works as an LC resonator, and you can see that the magnetic resonance basically occurs at the eigenfrequency omega m equals 1 by root LC. So, to the first order approximation, you can obtain the equivalent lumped elements of an LC circuit, where you can consider inductance to be equal to mu naught L square by T. L is basically this length, T is the thickness, okay. And the capacitance C is basically coming from epsilon naught, W is the width, T is the thickness, T is the gap between the split. Okay. So, what you see here, that all these physical parameters are giving you equivalent inductance and capacitance, and that determines the magnetic resonance frequency of your split ring resonator. Now, here we will do one thing, we will use A to denote the unit cell size of the single SRR, and this A will also serve as a scaling factor, right, because all the geometrical parameters such as length, gap, thickness and width, they will also vary in proportion to the unit cell size. Okay. So, if you consider this as your unit cell, everything will scale down with your unit cell size A. So, you can simply write that L and C both will scale with A, and with that you can find an important relation that the resonance frequency will basically scale inversely with the SRR size. So, you can write omega m equals C naught square root d by W L square, it will be proportional to 1 by A. So, more you scale, you can shift your frequency towards right. Now, this is a very simple expression, and it allows you the basic scalability, it tells you about the basic scalability of this kind of SRRs across various frequency regime, and you just need to remember that the resonance frequency is inversely proportional to the size of the unit cell of the SRR, right. Now, this simple but crude reasoning, however, is based on the assumption that perfect metal with infinite carrier density are being used. Okay. So, in this case, the current excited by the external field is basically carried by electrons with 0 electron velocity. But if you see in real metal, they will have finite electron density and hence a finite plasma frequency. Therefore, there must be a finite electron velocity also, which is proportional to the current I in the loop. Hence, you have to also think of an additional kinetic inductance, which is L kinetic kin, that will account for the total energy of the moving electrons, right. So, derivations will show that additional inductance L kin is also inversely proportional to the scaling factor K. So, as a result, the magnetic resonance frequency omega m will now take this particular form, that you need to write it as 1 over square root of L plus L kin times C. So, what happens, you will get L and L kin, you have the inverse proportionality with A. So, with that, and all these things, you can get into this particular factor, which will give you 1 over square root of A square plus constant. Okay. So, this constant is basically coming from the product of C and alkene, okay, which is the origin of the scaling saturation, okay, in the split ring resonators. Now, this will show that the maximum achievable resonance will be near 2 pi into 373 terahertz, that is typically around 800 nanometer wavelength, and that is where you can go maximum with this kind of single SRR approach, and that limits the SRRs at visible optical frequencies, right, because optical frequency is below 800 nanometer, typically between 400 to 800 nanometer, and this is where this kind of design cannot take you. Okay. So, an intrinsic limit to this scaling of SRR size for obtaining the magnetic resonance in optical range has actually pushed the researchers to break the barrier and look for alternative designs of magnetic meta atoms. So, the objective here is to find a structure that can fulfill the following requirement. First thing, it should be compatible with the existing nanofabrication techniques. Secondly, the magnetic resonance, if it is possible, get it excited by the external magnetic field directly, because that will give you much stronger magnetic response, okay, and you need to ensure negligible saturation effect at high frequencies, so the scaling is possible, right. So, an alternative structure people have thought of to the typical double split ring resonators is to like fabricate a staple like gold structure, okay, separated from a continuous gold film, as you can see in the figure. So, here the structure basically consists of an array of gold staples which are separated from a continuous gold film by a zinc sulfide spacing layer. Okay. So, this kind of staples will be interacting directly with the incident magnetic field and can give you a stronger magnetic response. So, here is an array of nanostaples with mid infrared magnetic response, and this is the time scale length scale that shows you the dimension of the nanostaples, right. So, this design basically maintains magnetic activity without suffering the drawbacks that you have seen in the scale down SRRs. Okay. So, from an equivalent circuit point of view, the upper loop of the staple, okay, this part, okay, basically works as an inductance, while the staple footing, okay, will serve as the capacitors, okay, and each staple can be viewed as a pair of staples facing each other due to the uniform gold film is basically acting as a imaging mirror, right. Now, the experimental demonstration basically used an array periodicity of 600 nanometer and a Lorentz resonance in effective permeability was observed, where a minimum value of minus 0.5 was recorded at 65 terahertz. Now, what you can see that the magnetic activity in this kind of nanostaple structure is much stronger than that of the planar split ring resonators that we discussed in the previous section, okay. Because the staples are basically standing up split ring resonators that could directly couple to the external magnetic field, okay. So, obviously, the standing up geometry will facilitate stronger interaction with the magnetic component of the light. In the previous case, it was the electric field who was giving you that magnetic moment. Here you are directly getting it from the magnetic component of the light. So, simulations have also shown that it is possible to extend negative permeability to higher frequencies of near infrared range, say up to 1.3 micrometer, by reducing the pitch size, that is basically the array constant or the lattice constant, and the dimensions of the arrays. Okay. More advanced artificial elements for magnetic metamaterials could include arrays of pairs of metallic rods, plates, strips. Okay. So, each of these structures is basically capable of supporting a principal eigenmode with an anti-symmetric current distribution in the coupled system. So, here is an example how it looks like. Okay. So, this kind of optical diamagnetic response was first predicted in pairs of metallic rods, okay, and that in 2002. So, a composite comprising pairs of parallel nanorods, as you can see here, okay, along with, so in this case this is the direction of the electric field, this is the direction of the magnetic field, okay, that is basically normal to this pair, okay, and this is where the field is incidenting, k vector. Okay. So, what is important that this kind of orientation is required. So, the magnetic field basically oscillates through the gap between the rods, okay, and it can excite a loop current, okay, in each pair of the rod like this. Okay. So, such a nanorod system may also exhibit negative index of refraction. So, this is a structure or composite. So, you can see this is a nanorod array that is in a dielectric medium, and this composite can give you optical diamagnetism, right. Now, in the actual fabrication of paired nanorod arrays using electron beam lithography and direct deposition, you will see that the cross section of each rod would become a thin rectangle or trapezoid kind of thing. That means, and you have to make sure that the thickness is kind of much smaller than its length and width. So, they are basically, this nanorod pairs are becoming like cut wire pairs or plate pairs, and this is how they are also referred to in the literature. Okay. So, sometimes square shaped plate pairs are also favored because this particular geometry eliminates undesirable polarization anisotropy in the metamaterial, right. And negative effective permeabilities from this kind of square nanoplate arrays have been observed at this near infrared range, which is from 1 to 1.5 micron, okay. And they have given negative effective permeabilities. Okay. So, one of the most successful magnetic metamaterial which was proposed thus far is a pair of metallic strips, which are shown here. You can see this is a gold strip, then you have a alumina spacer that is separating this bottom and the top strip. Okay. So, this is typically a trapezoidal cross section, and these are the two possible polarization. Here the magnetic field is along the length, so it is Tm. Okay. We can see that in the next one also. So, here you have the magnetic field along the length, and here you have magnetic field across this length. Okay. So, what you can see here that the nanostrip, these are called the nanostrip magnetic metamaterial, okay, which is made of this kind of a pair of metallic nanostrips which are separated by the dielectric spacer. So, here notice that the upper and the lower strip is not identical. So, the overall cross section of the strip pair is basically trapezoidal in shape, but this is basically coming because of the fabrication process. Okay. And under TM illumination, okay, you will see that the nanostrips show both magnetic and electric resonance, and the magnetic field is basically along the strip. Okay. But under TM polarization, you will see only the electric field is along the strip, and no resonance basically occur in this particular case. Now, fabrication of such nano strips are achieved typically using electron beam lithography and vacuum deposition. So, we will stop here in this lecture, and we will continue discussing about the analytical models and other details of this magnetic nanostrips in the next lecture. So, if you have got any query regarding this, drop an email to this email address mentioning course number and lecture number on the subject line. Thank you.